So we want to talk about the special relativity, which is basically the way we describe the space-time. So it would be good to start from Euclidean geometry and then make parallel, because basically everything that we are going to say in the special relativity is going to be have some counterpart here in Euclidean geometry, so it's easier to make connection. So what do we do in Euclidean geometry? Say we talk about two-dimensional Euclidean geometry, which is just a plane with coordinates x and y. And for instance, we can consider 2 points and talk about the Euclidean distance between these 2 points, A and B. Let's call that Euclidean interval IAB, that is defined to be, or I square, that is defined to be RA minus RB square, the Euclidean distance between these 2 points. If I want to write it in terms of these coordinates x and b, that is xa minus xb squared plus ya minus yb squared. Now when we define this Euclidean metric or Euclidean distance, then here we chose a particular coordinate system, this x and y coordinate system, to write it explicitly in terms of those. But there are some symmetries on this Euclidean plane, so we can change our coordinate system and still get the same answer. So we want to identify those symmetries, the symmetries that preserve the distance between the points, the relation between points, even though we might label them differently. So what are those symmetries? There are translations which correspond to translating everything, changing the origin of our coordinate system. So we define R tilde to be R plus A. Obviously, this translations cancels from the difference, so distance between the 2 points remains invariant on the translation. So this is one symmetry of this Euclidean geometry. And then the other one, which is a bit less trivial, is rotation. Which, if I want to write in terms of components, then it corresponds to doing a rotation, going to a different coordinate system, say x prime and y prime, or x tilde and y tilde, which such that the new coordinate system makes an angle compared to the original one. And so now what we have is that x tilde is equal to x cosine theta minus y sine theta, and y tilde is equal to y cosine theta plus x sine theta. Now, one thing that we are going to use a lot in this course is to use index notation, because things are going to become go on out of control if we want to write everything explicitly. So we introduce indices and summation conventions. So how do we introduce them? We say that Ri, we denote by components of the vector R by Ri. So R1 is gonna be x, and R2 is going to be y. And then this interval that I wrote here can be written as a sum over the components in this way, Ri, Rj times delta Ij. And then we use the summation convention, which is that every repeated index is summed over, so we don't write the sigmas anymore. We just write Ri, Rj, delta Ij. So this is the definition. When we write this, since I is repeated, it will be summed over, and will be summed over the number of possibilities for that index. Here, when we talk about two-dimensional Euclidean geometry, the possibilities are 1 and 2. In higher dimension, it will be from 1 to d. Similarly, for j, there will be a summation. Now, since this delta Ij is called the Kronecker delta, which is just a matrix which has 1 on the diagonals and 0 everywhere else. In fact, I can just remove this delta Ij and write this expression as Ri. Okay, so now if I use this index notation, then the rotation that we did here can be expressed in terms of the matrix of rotation. So we say R tilde I is equal to some matrix Rij times Rj. And the fact that rotations preserve, before saying that, in this particular case, for instance, we can see that this matrix Rij is a 2 by 2 matrix whose components are given by cosine theta minus sine theta, cosine sine theta, cosine theta. Now, the fact that we want these rotations to preserve our Euclidean norm, it means that R tilde I has to be the same as Ri. Remember, there are summation over I here on both sides. So what does it imply for these matrices? What it implies is that delta, okay, I don't write delta anymore, Rij times Rik has to be equal to delta of Jk. Because this relation has to hold for all R's, not a particular choice. So this is a condition that the rotation matrices have to satisfy. If I want to write it in matrix notation, that this relation can be written as R times R transpose is equal to the unit matrix, where R transpose is just defined by reflection with respect to the diagonal of this matrix. So R transpose Ij is equal to Rj. So the matrices that satisfy this condition, they are called orthogonal matrices. They can be defined in different number of dimensions. Here we talk about the two-dimensional case, but in general we can define them in any dimension. And they form a group, meaning that there is a set of these matrices, rotation matrices, or orthogonal matrices. there is a unit element in this set, which is unity. There is a composition law. There is a product of every two. If I have two rotation matrices and multiply them together, I get a third rotation matrix. And there is an inverse. For every rotation, there is an inverse rotation that brings us back to the unity, and that inverse is just this transpose. So here we are talking about rotations. Rotations are actually continuous, right? There is an angle here which is just a real variable. I can continuously go from zero rotation, which is an identity. I can continuously increase the rotation angle. So these are called continuous groups or Lie groups. Now we can consider the part of the group which is continuously connected to the unit element, and those in this case will be rotations. In general, the matrices that satisfy this condition, I call them orthogonal matrices, which form a group OD in these dimensions. If we focus on the subset or subgroup that is continuously connected to the unit element, those are called SOD. So for instance, there are the elements of OD which are not in SOD, they contain reflections. So those are not continuously connected to the unit element. Okay, so what else do I need to say about rotations? Another thing about the continuous groups is that we usually talk about their dimensions, the dimensionality of these groups, which is defined by the number of real parameters that we need to describe an element. So we said it's they are continuously connected to the unit element. So now you can ask, how many independent parameters do I need to define a rotation which is infinitesimally close to the unit rotation, which is no rotation. And for instance, in 2 dimensions, we just have only one angle. So the dimension of the dimensionality of SO2 is just 1. There will be only one angle that I need to specify. If we go to 3 dimension, then this is 3. Because we can have rotations along Z or along X or along Y. That's or in other words, 3 angles are sufficient to describe an arbitrary rotation. And then in these dimensions we can easily determine it. And the way we determine it in the dimensions is that we look at rotations which are infinitesimally close to unity. So a unit rotation will be that Rij just equal to delta Ij. This implements no rotation. But now we consider one which is which has some small deviation. That is small deviation I call epsilon Ij, and I impose this condition, linearizing epsilon. So if we impose that condition and linearizing epsilon, what we get is that epsilon Ij plus epsilon Ji has to be equal to 0, where epsilon Ij with lower indices is just defined in terms of by contracting with the Kronecker delta. So this is just delta ik times epsilon kj. Since delta ik is just a unit matrix, this epsilon ij with lower indices is really the same matrix as epsilon ij with mixed indices. So if you wanted to write it as a matrix, they would look identical. And so we have these conditions which tells us that this matrix epsilon ij has to be antisymmetric. So now we can ask what is the number of independent components of this antisymmetric matrix in d dimensions. If we had a general matrix in d dimensions, the number of independent components of that would be d squared. Now because of the antisymmetry, we have less independent component, and to determine that we can the number of independent components, so there is something has to be subtracted, the number of independent conditions that we have, which will be equal to any choice of two unequal indices of this matrix. Every choice of that would be an independent number, which is d times d minus 1 over 2. So we can check that in 2 and 3 dimensions it gives the right answer. So in 2 dimensions we get 1, and in 3 dimensions we get 3. One last thing about Euclidean geometry is that if we can talk about curves in this Euclidean plane. So what is a curve? It's just a collection of points in this plane. Which can be parameterized in some way. For instance, some r of lambda, where lambda goes from 0 to 1. That will be a curve. And one can ask about the length of this curve. So let's call this curve C. One can ask about the Euclidean length of this curve C. And the way we determine the Euclidean length of the curve is very easy. We just use that definition of the Euclidean distance. And what we do is that we divide this curve into infinitesimal elements, so that every element is approximately the straight line, and then we calculate the length of the straight line using the formula for a straight line in Euclidean geometry. We add them up and take the limit, so that the sum becomes an integral. So every element here, dl is given by the square root of dr squared, which is the square root of dx squared plus dy squared. And then if we integrate over this, we get the full length of the curve. Now given a particular curve, we can now apply this formula and calculate the length. For instance, if the curve is determined by some function y of x, then we can plug it in here and then calculate what is the full length of the curve. We can also define the unit tangent to this curve. So So the tangent to the curve is just a vector that is tangent to the curve. If I want to define the unit tangent, I use a definition of the line element, the Euclidean line element. So the unit tangent to this curve will be UR equals dxi or dRi divided by dl. And by this definition, what we have is that the norm of this unit tangent is equal to 1. Namely, if I calculate ui, uj, delta ij, that is equal to, by this definition of the length element, that is equal to 1. Any question about Euclidean or any things that I said so far? So the classical mechanics is based on Euclidean geometry for a space, but it treats time differently compared to a space. So time is absolute in classical mechanics, while a space has this Euclidean geometry. So one can talk about these transformations. In special relativity, we put time and space on more equal footing, and we talk about Lorentzian geometry, which is very similar to whatever we talk here about Euclidean, except that now the line element that we define is different. It's based on the Minkowski metric. So essentially, I'm gonna repeat everything that I said, except that now I and j go to mu1 mu, delta ij, which was the Euclidean metric, goes to eta mu nu, which is the Minkowski metric. Rotations go to Lorentz transformation. And then instead of the Euclidean length, we'll have proper time. Instead of the unit tangent vector, we will have the four velocity. So now we have time and space. On the board, I can only do 1 plus 1. So now, again, we consider 2 points in this the space-time diagram, A and B, and we define the interval as TA minus TB squared minus XA minus XB squared. So notice there is a minus sign here. I could put a factor of c squared here, the speed of light, which I set to 1 everywhere, so I don't write it. Now, again, we can introduce index notation. So we can talk about x mu, which is going to be t. Well, first of all, we have x mu, where mu goes from 0 to d minus 1, and 0 is time. So x mu can also denote t, x, y, z, etc. Then in this matrix notation, ID squared is minus eta mu nu xa minus xb mu xa minus xb mu, where eta mu nu is called the Minkowski metric. So it is the following matrix is minus 1 and then 1 along the diagonal and 0 everywhere else. So on this part it is just the usual Euclidean metric. So this interval, if we look at the equal time, if you look at equal times, then it is the same as the Euclidean interval that we have. So therefore, if we want to look for transformations that preserve this Lorentzian distance, they will naturally include the Euclidean transformations that we talked about at dimension d. Or maybe we can call it d plus 1. So this goes from d. D to 1 to d. Okay, so now, as before, we want to ask what are the transformations that preserve this. There are translations, as before, which now also include time translation. Of course, also in classical mechanics, time translation was a symmetry, but it didn't have anything to do with the interval, Euclidean interval that I wrote. Now it does have something to do with it, but time appears in this interval. But still, it's the symmetry of this interval. And then we can talk about the analog of rotations, which are the Lorentz transformation. And in this matrix notation, we denote them by lambda. So we have lambda mu nu times x nu. And when we put them together, we have Poincare transformations. So just these two together, they are called Poincare. The fact that this Lorentz transformation should preserve the interval, it puts a constraint on this Lorentz transformation similar to the constraints that we have on rotation matrices. Remember, they had to be orthogonal. R times R transpose had to be 1. So here you get a similar statement. Eta mu nu times lambda mu alpha lambda nu beta has to be equal to eta alpha beta. These are again orthogonal matrices, except that they are defined in a space-time rather than in a space. So when the signature of the metric is different. Again, these orthogonal transformations have the parts that is continuously connected to the unit element, which are called proper Lorentz transformations, and then the parts that are not continuously connected, and those include parity, reflections, space reflections, and time reversal. Our main focus will be on the proper subgroup, the part that is continuously connected to the unit element. Again, it's a continuous group. One can count the number of the dimensionality of the group, the number of independent Lorentz transformations that we have. And one can get a similar formula for it. Another important feature of this Lorentzian geometry is that we have a notion of causality, and that is because this metric is, or this interval is not sign definite, as opposed to the Euclidean interval, which was positive definite. This interval can be either positive or negative or zero, and depending on that we have a causal structure. So some definitions. Let's put A at the origin by doing a translation. Then we have points which are causally connected to A, to Alice, which are inside the light cone. And these are the points for which the interval that we define is positive. So here I is positive. There are points which are causally disconnected, which are space-like separated. And then there are points which are null separated, for which I is equal to 0. And that forms a light cone of the light cone of our observer or event or point. Then, depending on whether the point that we are considered, the space-time point that we consider has larger, as larger t compared to A, or a smaller t we call future or the past. And the proper Lorentz transformations, they never change this causal structure, meaning that if the point B is in the future of A, there is no Lorentz or no Poincare transformation, proper Lorentz or translation that takes B to the past of A, or make it space-like related to it. So this causal structure is preserved under Lorentz transformation. What is in the future of Alice is always in all frames in the future of Alice. Okay. What else? So we can also talk about curves in a space-time. By the way, these points in a space-time, they are called events. They are called events because they are events. They have a specific time and a specific location, which is what we mean in the usual language by event. And we can talk about curves, the collection of these events. And as before, we can ask about the length of a curve by, and we can define it by, again, dividing it into infinitesimal elements and adding them up. And every infinitesimal element is approximately a straight line for which we know how to calculate this Lorentzian length, and then we can add them up. So the total length tau is equal to integral d tau, and then d tau for every element is defined as, so in this two-dimensional case, is defined as dt squared, the square root of dt squared minus dx squared. So here I implicitly assume that I have a curve which is a time-like curve, for which this interval is always positive. You could define a length for a space-like curve, for a curve in which this interval, this infinitesimal interval, they all have negative lengths, Lorentzian length, in which case we would just flip this sign. But then it's not possible to define for a curve which is partly time-like, or partly time-like and partly space-like. So what else did we talk about? We talked about the normal, the tangent, unit tangent. So here there is also unit tangent. How do we define it? The unit tangent, we define it at every point to this curve. There is a vector dx mu by d tau, and this vector has obviously it is tangent to this curve when I take this limit, and it has unit norm in this Lorentzian signature, meaning that eta mu nu u mu u nu is equal to eta mu nu dx mu d tau, and this is minus 1 because of the definition of d tau squared. And this u mu is called the 4 velocity, or if we are in 2 dimensions, here the 2 velocity. So for instance, so what is the usual velocity that we are familiar with in the classical mechanics? We say v is equal to dx by dt. So now we can ask what are these quantities, how these quantities are related to the usual velocity. So for instance, d tau that we define here is equal to dt times the square root of 1 minus v squared. So we define gamma, the Lorentz factor, at 1 over 1 minus v squared. And in terms of the Lorentz factor, what we have is that dt by d tau is equal to gamma. And then dx by d tau is equal to gamma times v, which means that u mu, or here 2 velocity, is the following 2 vector, gamma and gamma. And now we can check explicitly that eta mu nu, u mu u nu is equal to minus 1. Now, if now there is a little bit of physics here, which is that this length, this Lorentzian length that we define, we call it the proper time, and we call it proper time because of the physical expectation that if we have a clock, if you have a good clock that moves on this trajectory, that good clock would measure that time. So this proper time is really the time that that clock measures. Now, questions like the one that we had at the beginning, like someone travels for 10 light years with some velocity and comes back, those I'm calculating the amount that astronaut ages during this travel would basically translate to calculating the length of these curves on this diagram. So in that particular example, we have someone that moves at a speed which is very close to the speed of light, and comes back, and when we ask how much she ages, that is basically asking what is the length of this curve, what is the proper time along this curve. So it's a purely geometric question. Any questions? Okay, so if there's no question, I can say a little bit about dynamics. So far it was just kinematics.
In the lecture there are problems in every chapter, right?
Say it again.
In the lecture notes there are problems at the end. Do you want us to also solve them, or is it only the...
Those are optional. If you like, you can solve them for yourself.
Okay.
In fact, you are encouraged to solve them for yourself. If this is your first exposure to the material. If you know it, then you know it. Okay, so we can also talk about relativistic dynamic. So when we introduce this notion of relativity, what we basically require is that all inertial observers, meaning that all of the observers who are related by this Poincare transformation, they should see the laws of nature to be identical. What does it imply? They should have the same underlying description of physics, fundamental laws of physics. What does it imply? It implies that the laws of physics have to be written in a way that we call them covariantly, meaning that the form of these laws of physics should remain the same in all frames. Therefore, if we have laws of physics or equalities between different quantities, they should equate quantities which transform in the same way under Lorentz or Poincare transformation. So what are these transformation properties of quantities? Again, this is similar to the Euclidean case. In the Euclidean case, we had the scalar quantities, we had vectors and tensors and so on. So here is the same thing. We have scalars, vectors, tensors, and so on. The transformation properties are basically determined by the index structure. So basically, when the indices match, we have the right equation. Now, in particular, we can talk about some very fundamental law, which is the conservation of energy and momentum. And in relativity, that conservation is expressed in a single formula, which is the sum of the momentum for vectors for initial particles have to be equal to the sum of the momentum for vectors for the final particle, where the momentum for vector is defined as the rest mass times the for velocity. What is the rest mass? Rest mass is the mass of the mass of the object when we go to the frame in which this is instantaneously at rest. So this is a quantity that is uniquely defined. It's just the scale is a number, therefore it's a scalar quantity. And u mu is what we defined before, is the for velocity. Now we can ask why this equation should be valid. Obviously it has the right structure to be valid because it's relating 4 vectors to the 4 vector. But also when we write the laws of nature in this new, not so new relativistic theory, we want them to agree with the laws of nature that we know before in the right limit in the classical mechanics. So for instance, we can check that this equation that we have written here, if we take the non-relativistic limit, it will reduce to the energy and momentum conservation that we are familiar with in non-relativistic mechanics. And that is because this momentum for vector is m gamma v if we go to the limit in which the velocity is much less than 1. Remember, the speed of light is set to 1 here. Then we have P mu given by m plus 1/2 mv squared plus however the correction in v, times fourth order in v, and here we will have mv just cubic and higher order tensor in V. So therefore the spatial component of this equation becomes the conservation of the three momenta, and the time component of the equation effectively reduces to two equations. One is that the sum of the masses are conserved. So we never change the number of particles in non-relativistic processes, because the rest energy is always much bigger than the kinetic energy of the constituents. So the masses remain the same between initial and final state. Once we infer that, then we will also have the conservation of the kinetic energy. So then we get the sum of initial kinetic energies equal to the sum of the final kinetic energy. Of course, here I'm talking about the scattering process where there are initial particles with no interaction and final particles with no interaction. So the energy is just determined by the kinetic energy. We can also define four force, or in any number of dimensions d force, as a generalization of the concept of force in Newtonian dynamics, and this is defined as p mu d tau, which is a 4-vector, because p mu is a 4-vector and tau is a Lorentz scalar. And this is a good definition, or this is a good quantity to be called a force, a forward force, because if we go again, if we take the non-relativistic limit, then in some sense it approaches what we call the force in Newtonian dynamics. How do we see that? So we can ask what is the this what is this force if we go to the rest frame. So the rest frame, we define it as a frame in which the particle is instantaneously at rest. So if we look at the spatial component of this object, what we have is d squared eta squared times xi. Now let us remember that we had dt by d tau is equal to u0, which is gamma. So we can write this as, we can use the chain rule to write this as m gamma d by dt of gamma dxi by dt. And then this is m gamma squared d2xi dt squared plus m bj dbj dt times dxi dt. But if we go to the rest frame, so remember this was just the ice component of this force. So if you go to the rest frame where the velocity is equal to 0, this last term vanishes and we get Fi in the rest frame, and gamma is equal to 1. So in the rest frame, V is equal to 0 and gamma is equal to 1 instantaneously. Notice that this does not mean that dV dt is 0. That can be non-zero in general. Okay, so what we get is the usual expression for the Newtonian force. So this quantity that we call it the force, indeed it reduces to the Newtonian force if we look at its spatial components. Similarly, you can define for acceleration by just not writing this m here. And that for acceleration, as we take the Newtonian limit, it reduces to the usual acceleration. Then we can easily show that in the rest frame, the zeroth component of this for force or for acceleration is equal to 0. Therefore, we can talk about proper force or proper acceleration as the square root of a mu, and this quantity is just the usual Newtonian acceleration measured in the instantaneous rest frame of the object. So this square root is equal to a Newtonian square. In the rest frame. Okay, probably we can stop here. The next thing will be to do some exercises with observers with constant acceleration. The so-called Rinder observer. Is there any question?